All right, THS Chem Squad. Here's your next round of video notes coming at you. This is all about oxidation numbers, and you'll be writing this directly into your notebook on the page provided to you by your teacher. Let's go ahead and get started and take a look at what oxidation numbers are. All right, so oxidation numbers are the apparent charge on an atom in a compound. So we've actually already talked a lot about charge earlier in the year, and now we're going to take this just a step further and look at some more complicated compounds and look at each individual atom's charge or apparent charge that they would have in that compound. Some of these rules are going to overlap with things that we've already seen, but if you recall looking at your periodic table, some elements have a lot of numbers in the upper right-hand corner of their box on the periodic table, which means they have multiple oxidation states. And all we've dealt with so far are the first oxidation state, the normal one that most elements have. Okay, so now we're going to go through a few rules here to get these oxidation numbers, and some of these are going to make sense with things that we've already done. So this is a little bit of review, and then we're just adding a little bit of extra to it to determine some of these oxidation numbers. First rule, uncombined elements have an oxidation number that is going to be equal to 0. They're going to have 0 as an oxidation number. So this means when you find an element in its natural state, it does not have an apparent charge on it. It's not an ion, so it's going to have oxidation number of 0. So for example, if you're given the formula for just sodium, it would be Na because it's a monatomic element, and its oxidation number would be 0. Typically, you're going to see it written above the atom or the element, just like we would a charge. Chlorine gas, or chlorine in this case, Cl2, it's still in its natural uncombined state. It's one of those magic 7 elements that come in pairs, or the diatomics. So that's also would have an oxidation number of 0. All right, the second one, monatomic ions have oxidation numbers equal to their charge. So this is what we were doing in the past. We talked about ionic compounds and crisscrossing charges to create the correct formula. In this situation, the oxidation number is the same as what we would do if we normally found the charge. So for example, sodium chloride, NaCl, we know that if we were going to actually do the reverse of the crisscross or figure out what charges these had, we would look on the periodic table, and sodium is a +1 and chlorine is a -1, and we get that from the periodic table, the very first number that we see. Same idea with calcium chloride. Calcium is a group 2 element, so that's a +2. And chlorine is a -1. So remember when we went through and crisscrossed them, that 2 would come over here, the +2 would come down next to the Cl to give us 2 chlorines, and the 1 comes over here next to calcium, and we get a overall neutral charge for our ionic compound. Number 3, group 1 is always going to be a +1 and group 2 is always going to be a +2. So whenever you see those in a compound, their oxidation number is consistent and it's always going to be the same. Number 4, fluorine is always a -1. No matter when or wherever fluorine bonds, it automatically gets a -1 charge. And this is because fluorine is the most electronegative element on the table. So it goes back to those trends we talked about a long time ago on the periodic table. Fluorine is the most electronegative, meaning it always will pull the hardest and attract electrons more. So it always attracts that one electron to get a stable outer shell. So no matter what is bonded with, fluorine always has a -1 oxidation state. Number 5, hydrogen is +1 unless it's bonded with a metal, then it's -1. We typically don't see this, but if it were to come up, it's a -1 and it's with a metal. So almost always we're going to see hydrogen in front of other elements or with carbon, and in that case it's always going to have that +1 oxidation state. Let's say we saw an example like lithium hydride. In this case we have a hydride and it's you see how it's second in our formula with a metal first. It's going to actually have the oxidation state of -1. Doesn't happen very often, but if it does, a metal will cause hydrogen to have an oxidation state or a charge of -1. 6. Oxygen is -2 unless it's bonded with fluorine. Again, oxygen is the second most electronegative element, so it's always going to be -2 unless that rare situation when you see it with fluorine. And in that case, it's going to change because fluorine is more electronegative, so it actually pulls on the electrons better than oxygen. So oxygen's oxidation state will change. 7, the sum of the oxidation numbers will equal 0 in all compounds. And this goes back to what we talked about with ionic bonding. Whenever we are trying to figure out the charges on our ions and put our formula together, we have to make sure that overall we get a neutral compound or a zero charge, which is why when we looked at sodium chloride, we had our +1 and our -1. If we put both of those together, they cancel each other out to get an overall charge that is equal to 0 or neutral. Okay, if we were looking at number 8, the sum of the oxidation numbers on an ion will equal the charge on that ion. So since this is not a neutral, nitrate here is not a neutral compound, it is an ion. It's got that -1 charge. Whenever we add up the oxidation numbers, it will equal that value of -1. Okay, so this is how this works. If we look at the rules we have just written down, we know that out of the rules we wrote, oxygen will always have a -2 unless it's with fluorine, and it's not with fluorine. So that means oxygen is a -2 oxidation state in this ion. Okay, let's look at how many of those we have there. In nitrate, we have 3 oxygens. That means we have -2 3 times. That's a total of -6 coming from just the oxygen. So that's just for oxygen. So now the next step is to figure out what exactly would nitrogen have as an oxidation state. Well, we know that if oxygen is a -6, and if we add, the sum tells us we're adding, if we add all the oxidation states, we're going to get to the charge of the ion. The charge of our ion is -1. So if we know we have -6 coming from oxygen, and X is going to be what is the one nitrogen value, -6 plus X gets us -1. So in this case, nitrogen is going to end up having an oxidation state that is +5. So if you were to look on the periodic table and find nitrogen, you would see that one of the possibilities that it has for an oxidation state is +5. It's further down the list. It's not one of the first ones, but it is a possible oxidation state. So if we were to add up all of our oxidation states this way, we would get to that charge of -1. All right, so let's look at a few examples here. So the first one, if we had to figure out the oxidation state for each atom in sodium nitrate, NaNO3, look through our rules that we just went through. I see that I'm starting with sodium, which is a group 1 metal, and group 1 is always going to be +1. And then I also see that oxygen is in here, and it's not with fluorine, so that makes it a -2. Nitrogen is the tricky one because it's in the middle, and it's not one of the ones we made a rule on, so we have to kind of figure out and work our way backwards and figure out what nitrogen would be. So this is a neutral compound because it didn't have any charge at the start, which means all of my oxidation states added up, the sum of them needs to get to 0. So I know that looking at what I have so far, sodium is giving me a +1. Oxygen is giving me -2, but there are 3 of them, so I'm going to multiply that by 3. And then what's left is I have 1 nitrogen to fill in. So I got to figure out what is nitrogen's oxidation state. And overall, when I add all these up, I have to get to 0. So if I were to do that, that means solving for x is, again, is going to equal positive 5. That means the oxidation state on nitrogen, which is the harder one to see in this case, is going to be positive 5. All right, so I did the harder one. What I would like you to do is try H2O and CO2 and figure out the oxidation states for those two substances. Good luck, give it a shot, and bring any questions with class to you tomorrow. Chem Squad out.